Okay, so let's look at another way that we can determine the empirical formula of a compound, and that is if we know the percent composition of the various elements that are in that compound, okay? And so the best way to look at this is just to do an example. If we go to page 242, example 8.6, we see that a substance is found to be 40% calcium, 12% carbon, and 48% oxygen. And the question is, what is the empirical formula? Well, we don't have grams, we're not given moles, anything like that. The stuff that we used in our last section to determine the empirical formula. But we can actually figure out the number of grams based on this, right? Because let's assume that whatever this substance is, let's assume that we have 100 grams of that substance, right? So if we have 100 grams of this unknown substance, and this is the percentage of that unknown substance, then that means we have 40 grams of calcium, right? Plus 12 grams of carbon, plus 48 grams of oxygen, right? That gives us a total of 100 grams of our unknown substance. So these are the numbers that we can use to determine our empirical formula. All right, so I'm going to write those down. 40 grams of calcium over here, 12 grams of carbon, and 48 grams of oxygen. And we'll make some more room. All right, so from that, we can determine the number of moles of each substance that we have, right? So if we've got 40 grams of calcium, then we look at our periodic table, and then we know that for every 1 mole of calcium, we have 40.08 grams of calcium, right? And so that's going to give us 0.998 moles of calcium. So we'll just go ahead and write that down here. So 40 grams is equivalent to 0.998 moles. And then 12 grams of carbon, 1 mole of carbon has a mass of 12.01 grams. And so that's 0.999 moles of carbon. We'll write that down here. And then finally, 48, if I can squeeze it down the bottom here, 48 grams of oxygen. 1 mole of oxygen is equal to 16 grams of oxygen. And so that is equal to 3.00 moles of oxygen. Okay, we'll write that down here, 3.00 moles of oxygen. Now, given that, we can do what we did before and determine the ratios of each of these substances. Again, we're going to find the ratio to the smallest one, right? So in this case, that's calcium. So the ratio, let's see if I can actually write ratio this time. I did. Ratio of C to Ca is going to be equal to 0.999 over 0.998, right? So that's going to equal 1. And then the ratio of oxygen to calcium is going to be equal to, we have 3 moles of that, so 3.00 divided by 0.998, and so that's going to be equal to 3, right? So our final formula is for every Ca, there's going to be 1 C. That's where that 1 represents there. And for every Ca, there's going to be 3 oxygens, right? So this is our empirical formula for our unknown substance. Now we can also go in the other direction, right? What if they give us a formula? What if they give us an empirical formula and say they want to know what the percent composition is of that substance? And we can do that as well. So example 8.7 asks that question. What is the percent composition for each element in Na2SO4? Na2SO4. This one's actually a little easier. We don't even have to deal with grams in this one. we just figure out the atomic mass of Na2SO4. So Na2SO4, we go to our periodic table and we see that sodium has a mass of 22.99, so we have 2 sodium atoms in our formula, so 22.99 AMU is what that is, right? Plus 32.6, that's sulfur, 32.06, sorry, AMU for sulfur, and then finally plus 4 times 16 AMU for oxygen. And that gives us a total AMU for our substance of 142.04, not a total AMU, I'm sorry, a total atomic mass in AMUs of 142.04 AMUs, okay? So we'll write that down right here. The total is 142.04 AMU. That's what we just calculated the atomic mass of Na2SO4 to be. So, what's our percentages? Well, the percent then of Na is going to be equal to, we have 2 Na, so 2 times 22.99 AMU, divided by the total AMU, 142.04 AMU. And so Na is going to, whoops, we need to multiply that by 100 because that's going to be a decimal, times 100. So Na is going to comprise 32.37% of this compound. All right? What about the percent of S? Percent of S, 32.06, because we only have 1 sulfur atom in the compound, divided by the total atomic mass, multiply that times 100, and so that's going to give us 22.57%. That's the percent S. And then finally, the percentage of oxygen in this compound is going to be, we've got 4 oxygens, so it's going to be 4 times 16 AMU divided by 142.04 AMU times 100 to give us a final percentage of 45.06%. All right? And so if we punch this in our calculator, if we did this correctly, when we punch this into our calculator, we should get a number that's very close to 100%, right? Because of the way we round and, you know, all of that stuff, that significant figures and so forth, it may not be exactly 100%, but it should be really, really close, right? Maybe just 99.98% or 100.02% or something like that. But if you add these numbers up and you don't get a number close to 100%, then you did something wrong. You need to kind of back up and look at it again. But that's how you would determine the percent composition if you're given the empirical formula at the beginning. All right? So that's kind of our talk on empirical formula, on determining empirical formulas. And next lecture, we will talk about polyatomic ions. Ooh, I know you can't wait. We'll see you then.